All right, so last time we took it a step further after our discussion in the first two lectures. We talked about random variables. We talked about the expectation. We talked about the moments, the variance. We talked about discrete random variables and their PMFs, the continuous random variables and their PDFs. We talked about CDFs and some famous discrete and continuous random variables. On the discrete side, we talked about the Bernoulli, the binomial, and the geometric. On the continuous side, we talked about the uniform, the exponential, and the Gaussian, right? So today, we will move on another step further, and we'll start by talking about functions of random variables. So what are the generic steps that you should follow in order to get to a CDF and a PDF of a function of a random variable? There are some shortcuts we will talk about later on, but let's talk about the generic way. So we start by finding the CDF. And let's here talk about a generic function y equals g of x. How to find the CDF? Fy of y is the probability that y less than or equal to y, is the probability that g of x is less than or equal to y, under the condition that if g inverse is unique, we can immediately write Fy of y as fx, or the probability first. Let's do it using probability. The probability first that x is less than or equal to g inverse of y, which is essentially fx of g inverse of y. And then find g inverse of y and continue to get Fy of y. And the last thing is to differentiate Fy of y to get small fy of y. All right, so what is going on here? Let's talk about it in a little more detail. The CDF, Fy of y, is the probability that y less than or equal to y. This y is a g of x less than or equal to small y. If g is invertible and unique, this method is the smoothest. So essentially, you invert a function. We will show examples today about how to invert a function. And thus, Fy of y becomes the probability that x less than or equal to the g inverse. And thus, this is a CDF itself, right? And its argument is y, okay? Remember that these PDFs and CDFs, the function itself is function of what is between the brackets. It's function of the values itself. It's not function of what is written here, okay? X just gives you what CDF is this, all right? The capital X, I mean. And then find this g inverse of y, continue, and then differentiate. One direct method here is you can directly do the following. Fy of y, that's the PDF immediately, is summation over k, fx of xk, the differentiation dx by dy at x equals xk. Okay. Can anyone find the relation between this and what we have been doing here until this step? Is there any relation? Can you relate this thing to this thing? What would you do to get to Fy of y from capital F? Differentiate, right? If you differentiate this, shouldn't it end up being something that looks like this? At least if you have only one xk, right? It will look like what using the chain rule? It will be the PDF multiplied by the differentiation of what is between the brackets with respect to y, right? So if you have a unique xk, this thing is this thing. It's the same thing, okay? And we will show an example where they are not really unique. So here, each xk is a possible G inverse of y. You can even call it G inverse K of y. Okay, this is all for continuous random variables. Obviously, I mean, the whole CDF thing is not particularly for continuous, but it's better to use it for continuous random variables. What can we do if the random variable is discrete? There are two scenarios, assuming that we have already reached it here. What shall we do if the random variable is discrete? So instead of the differentiation, it will be? What's up? Difference, right? Absolutely, right? So instead of the differentiation, it will be the difference. But in fact, there is one quite big advantage for discrete random variables. That for discrete random variables, the main function characterizing them is a probability describing function. The PMF is a probability describing function. It refers to the probability that y, capital Y, equals small y. So you can immediately substitute into it and do the algebra inside it. You cannot really do that with the PDF because the PDF is not a probability. What is Fy of y? It's not the probability that capital Y equals small y. And that's why you need to go to a probability and differentiate it. And the probability in the continuous case is the CDF. You go to a probability, then differentiate it. But for the discrete random variable, you can directly try to play with the probability that y equals y. All right? Awesome. Let's do an example. Example 1. Let random variable y be defined as y equals x squared, where x is a continuous random variable with known distribution. Find the CDF and the PDF. Solution. Let's do the traditional way first. Let's try to do it like this first. So Fy of y is the probability that capital Y less than or equal to small y, is the probability that x squared less than or equal to small y. Is G inverse here a unique function? Another question is, how would you deal with this? You can answer any question of the two. If you have function f of x equals x squared, the inverse function, is it a unique function? If you have this guy, is f inverse of x a unique function? No, right? There are two functions that can give you the answer, right? Okay? Square root x minus square root x are both appropriate functions, right? So the inverse function here is not unique. So how can we deal with this guy in terms of probability? We can just like write it this way. Everybody's okay with that? If x squared is less than or equal to y, so x is between minus square root y and square root y, right? How can we get this in terms of the CDF? Exactly. This we did together last time. So this is fx of square root y minus fx of minus square root y. All right? The range of y, it is greater than or equal to 0. Y equals x squared, obviously, would take only positive values, right? Non-negative values. It can be a 0, of course. All right. So for y less than 0, fy of y is 0, and thus fy of y is 0. Let's differentiate this thing. So fy of y is d capital F y of y by dy. How to differentiate this thing? It's the differentiation of whatever is inside the brackets, and this becomes a PDF, right? Okay? So this directly becomes 1 over square root y times 2 fy fx of y fx of square root y plus fx of minus square root y. Everybody's okay until now? Mm-hmm. Okay, now let's try to do it using the direct method. In the direct method, we try to get the inverse function. So here we were saying that you have g of capital X being x squared, which is y. You can write it as g of x equals x squared. How can we get the inverse of a function? In general, not even this thing, but in general, how do you get the inverse of a function? You replace the variable by the function you are seeking, and you replace the function by the new variable, right? So here you can write y equals g inverse of y overall squared, and thus you have x1 equals g inverse 1 of y equals square root y, x2 equals g2 inverse of y equals minus square root y. Everybody's okay until now? Okay. These x's are possible inverse functions. As simple as that. Okay? And thus we directly substitute in this relation fy of y equals summation from k equals 1 to 2 fx of xk, the differentiation dx by dy at x equals xk, which immediately also gives us 1 over 2 square root y fx of square root y plus fx of minus square root y. All right? Until now, do you have any problems? Everything is good? Okay. Okay. Now, you are going to become dangerous people. We will learn something that will make us dangerous. So, at the moment, you can sit on your chair, do some MATLAB programming, and generate a continuous random variable of any distribution, Gaussian, exponential, whatever you want, right? However, inside that computer program, things don't really work like that. The MATLAB and the computer in general is a discrete entity. Continuous entities exist in life, exist in nature. But the MATLAB operates on discrete data. You give it samples, it generates something. How can you generate something to be continuous using MATLAB? Is that you reduce the steps between the samples you are taking so much so that they become almost continuous. All right? Under this understanding, you can enter any PMF you want to MATLAB because PMF is discrete. You tell the MATLAB the probability of this point is that, this point is that, this point is that, done, right? But you cannot do that for the continuous case. There is only one random variable, one continuous random variable that is being generated by default with its PDF and CDF inside the MATLAB, and that is the uniform random variable between 0 and 1. So how can the MATLAB generate the other random variables? That is what we will do now. Okay, example 2. Computer generation of random variables. Suppose you have U as a uniform random variable in the interval 0 to 1. Find G of U such that X equals G of U is exponential with lambda. Is the question clear? You have a uniform random variable. You want a function of the random variable such that the generated random variable from the function of u is exponential with lambda. Okay? We will do something generic first, and then we will see how it can help us to solve the problem. Let u equals h of x equals fx of capital X. What is this? We are used to fx of small x, where small x is the value and stuff, right? What is this? What does that mean? What is f capital X of capital X? Exactly, right? So that is a function of the random variable. You take the CDF as a function. It's just a function. And you use the variable of the function to be your own random variable, right? So fx of capital X is a function of the random variable capital X. What does that mean in reality? You are sampling this random variable, taking samples from this random variable. Now we are talking not from a mathematical perspective. We are trying to look at it from a more practical perspective, that you are taking samples of the random variables and injecting it into the CDF of the random variable, okay? Samples from the random variable, injecting them in the CDF of the same random variable, all right? Okay, let's see what this can lead us to. Fu of u is the probability u less than or equal to u, which is the probability that fx of x is less than or equal to u, which is the probability that x less than or equal to fx inverse of u, which is fx of fx inverse of u. What is this? Thanks. Exactly. What is the range of u? Also exactly. Why? Because u is a CDF. That's what you... So u is a CDF, so u has to be between 0 and 1. Okay, what is the only random variable that has its CDF being u, where u is between 0 to 1? What is the only random variable that has its CDF looking like this? Even if you have doubts, if you have its CDF, how to get the PDF? Yeah, when you differentiate this, you get what? Exactly, right? So even if you are confused about it, differentiate this guy, you get this guy. Question for you. Did we make any assumption of any type about the random variable x other than x being a continuous random variable? Did we make any assumption? No, did we make any assumption about capital X? Just from what you see on the board? No, right? We didn't make any assumption about capital X. What is this telling then? We picked a generic continuous random variable x, took samples from it, substituted them back to its own CDF, and the result was a uniform random variable from 0 to 1. All right, let's write that down and see from where we can get after that. Sure.
How did we test the second last step? Yes.
How did I get to this step?
Yes.
From this step? It's just that if a function is less than or equal to u, the inverse of the function is less than, so this is a function, right? inject the inverse to both sides. Do this operation. Right? Oh, of course. Okay, so what is this? Therefore, U equals fx of x is uniform 0 to 1 for any continuous random variable x. Wow. So we just took samples from a generic continuous random variable, we put them back into its CDF, we immediately got a uniform, regardless from the random variable. All right, this is magic, but still we don't know how it can help us to solve our problem. We still didn't get this exponential. Any suggestions? How can we get the exponential given we reached this fact? So you know that you take x, put it back into its CDF, it gives you a uniform. But you have the uniform already in the computer and you want to get x. How can you do that? Again, u is fx of x, but you are targeting x itself, not u, right? Okay, so x will be f inverse x of u. That is just by taking the inverse of both ends, okay? But you know the CDF. You know it. You know the CDF of these random variables theoretically, and you can implement a function in MATLAB. So the two ingredients you have are, number one, you can generate a uniform in MATLAB. Number two, you can enter a function in MATLAB. You don't have any problem with that. These two pieces of information, in the end, will give you the random variable you want. The fact that you can generate uniform, the fact that you can implement a function, okay? So the only step missing is to get the CDF inverse. Once you get the CDF inverse, problem solved. Okay, what is the CDF of an exponential random variable? What is capital Fx of x for an exponential random variable? It is this guy, right? Right? You remember that its PDF was lambda e to the minus lambda x, right? Okay? So it's 1 minus e to the minus lambda x, lambda greater than 0, x greater than or equal to 0. Again, we can call this thing, we want to get its inverse, so y equals 1 minus e to the minus lambda g of y. What did I do here? This becomes the variable, x becomes the function, because we want to get the inverse. And thus, lambda g of y is minus ln 1 minus y, and thus g of y is minus 1 over lambda ln 1 minus y. G of y is fx inverse of y, and thus g of u is fx inverse of u, which is minus 1 over lambda ln 1 minus u, which gives us the random variable we want, x. What did we do here? We had a CDF. A known CDF is just a function. We got the inverse of the CDF. This inverse here ended up being g of y is minus 1 over lambda ln 1 minus y. And we know from the beginning is once we get the inverse CDF and inject u, the uniform random variable, in the inverse CDF, we get x, the random variable we want. And thus fx inverse of u is minus 1 over lambda the ln, which is the random variable x. All right? Any problems with this? Everything is clear? This is exactly how MATLAB and all of these programs generate continuous random variables of non-uniform distribution. The idea in one sentence, generate the inverse CDF. And that's it. All right? Good. Let's do the transform methods. So first of all, a rule about the expectation of g of x is the integration over x, g of x small, fx of x dx, obviously for a continuous random variable, and it's a summation if discrete. The characteristic function is fy of omega, which is the expected value of g omega capital X, which is the integration over x e to the j omega x fx of x dx. And this is also for primarily continuous random variables. And how to generate moments from it, the expected value of x to the n is 1 over j to the n dn by d omega n phi y of omega at omega equals 0. All right, two things. Number one, have you seen a similar equation to this before? So you don't answer a lot because of the recording? I mean, go ahead. I mean, you are the ones watching this anyways. The Fourier, right? That's the Fourier transform, right? Ah, with one little difference. What's up? Well, yeah, if you are, yeah, well, for this particular case, when you are going from the time domain to the frequency domain, it doesn't have it. It has it when you are returning, right? Because here you are integrating with respect to the time. But there is one little difference here in this guy. It has a minus sign, but I mean, it's a minor difference, seriously. Having said that, all the properties of the Fourier transform from the time domain to the frequency domain, from the frequency domain to the time domain, also apply to the characteristic function from the PDF of a random variable. That is, if you have the convolution between two PDFs in the probability domain, the result will be convolution leads to multiplication in the characteristic function. So convolution in time, multiplication in frequency. Differentiation results in the multiplication of j omega from a domain to another. Differentiation in the other domain, in the frequency domain, results in a multiplication in t in the time domain, and so on and so forth. The same set of properties. All right? Which is a lot of fun because also it gives you the advantage of, or the ability of solving in the characteristic function domain, between quotations, the frequency domain, instead of solving in the probability domain itself. All right, second question. Any idea how can we get to this from here? Thank you so much. Absolutely. Perfect. So you do the expansion around the 0. Forget about the expectation for now. So the expansion of this guy is 1 plus j omega x plus j omega x squared over factorial 2 plus j omega x cubed over factorial 3 dot dot dot. Then you enter the expectation here. It becomes the expectation of all of this. Through linearity of expectation, you do separate these terms. One step will be remaining, the differentiation, okay? For simplicity, we will try to illustrate it on an example, and after we do it on an example, it will be clear. Let's assume that you are trying to get the expected value of x cubed. To get the expected value of x cubed, you will differentiate 3 times, right? Differentiation 3 times will cancel out this term, will cancel out this term, will cancel out this term, all right? The only term that will remain is this term and the terms following it. When you put omega equals 0, all the terms following it will go away. That's the only term that will not have omega after the differentiation, all right? So what is the only thing remaining? The division by j to the n, right? So this is how to get this relation from the fundamentals. That is about the continuous random variables. How about the discrete random variables? We have the probability generating function. For non-negative discrete. So g x of z is the expected value of z to the x is summation over x z to the x px of x. All right, generating probabilities will be px of x is 1 over factorial x, dx by dz to the x, the gx of z at z equals 0. The same question once again. Have you seen our friend here before? Who's talking? Exactly. That is the z transform, right? That is the z transform. The same issue with a minus sign. Okay, we have ignored it by now. Question for you. The z transform, or just look here. So we know that px of x is a discrete function, right? This is a PMF. It's a discrete function. Would that result in gx of the z as well being a discrete function? So px of x is a discrete function. How about gx of z? Is it a discrete function in z? Is the z transform in general a discrete function? Is the discrete Fourier transform in general a discrete function? No, absolutely not. Absolutely not. When is the case where the discrete Fourier transform will end up giving you a discrete function? I know you get confused by the many terms, DFT, DTFT, FT. I get that, I get that. But in general, the way I try to go about these things, and I hope we build this intuition together, is that yes, knowledge is important, but the more important thing is how to get to the knowledge. How to get to the knowledge is more important than the knowledge. I have come to know very famous professors, celebrated names, whom you can ask a question in things they did, not somebody else, they did, and they end up just like getting a marker and trying to derive it in front of you. How to get to the knowledge is way more important than the knowledge. Let's return to our question. As our friend here said, in general, the z transform does not necessarily need to be a discrete function of z. In fact, in this case, it will never be, and we will say why. And the DFT is also not necessarily a discrete function. What is the case under which the DFT will end up giving you a discrete function in terms of the frequency? Thank you so much. That's if the time domain signal is periodic. Because periodicity results in concentrating the identity of the signal into certain frequencies that get repeated. This is the fundamental idea, right? So only if the time domain signal is periodic, that discrete time domain signal is periodic, would we have its DFT. It's the discrete time Fourier transform. It's the DTFT, not the DFT, because the DFT by nature operates on periodic discrete signals anyways. So only in that case is the Fourier transform of it, the discrete time Fourier transform will end up giving you a discrete function. Periodicity in time results in having a discrete function in frequency. Okay, let's return to this situation then. Will this thing ever be periodic? It's finite. How can it be periodic? Periodicity implies that the signal is infinite. This guy is finite. It has to sum to 1, right? It is finite. It can never be periodic, even if it looks something like this, where you could sum it to 1. It's still aperiodic. It will never be periodic, right? So in that case, the probability generating function in general is a continuous function in Z, not a discrete function in Z. All right? Okay. Let's do an example. All right, example 3. Let y equals ax plus b, where x is Gaussian with m and sigma squared. Find the characteristic function of y. All right, fundamental step at the beginning, phi y of omega is the expected value of e to the j omega y is the expected value of e to the j omega ax plus b. Can we simplify this guy a little bit?
We can take e to the j omega b also.
Exactly, this is a non-random quantity, so e to the j omega b, the expected value of e to the j omega ax, which is e to the j omega b, the integration. Well, we can actually try to get this guy directly and then return to this equation. Let's try to get this guy. The expected value of e to the j omega ax integral from x equals minus infinity to infinity, e to the j omega ax 1 over square root 2 pi sigma e to the minus x squared e to the minus x minus m squared over 2 sigma squared dx. Okay. This integration is ugly, like very ugly, right? I mean, you have exponential x squared, 2x, and another x in the outside. That doesn't seem like the best case scenario to have. So let's look at the exponent alone. The exponent in this case is minus 1 over 2 sigma squared, x squared minus 2mx plus m squared minus 2 sigma squared j omega ax. How can we deal with this thing? How can we deal with this thing such that we end up creating a solvable integral here? Thank you. Thank you, exactly. So completing squares and sums of squares, these are like branches in mathematics for how wonders you can make with them. Exactly like what our friend here said, you complete a square here. When you complete a square here, you could get a solvable integral here because you will be integrating a PDF from minus infinity to infinity, which is 1. Right? The other question, how can we complete a square here? How can we complete a square here? So I'm going to be writing this as follows: x minus something squared plus something else. What should we have here? You could try to complete many squares in this scenario. But there is only one square that would be useful to you. A square where you have every single term that relates to x. If you leave some x's in some exponents outside, then you didn't do anything. And still the integral is quite complicated. So you got to take all the terms that pertain to x in one square. How to do that? Like our friend said, you have this, and this together. And thus, this is going to be m plus j omega a sigma square. All right? Square of the first, 2 the first times the second, and then square of the second. Until now, all these terms we have with us. But we have added 2 extra terms. Those 2 extra terms are resulting from the square of this thing, right? Which is 2 times this and the square of this. So whatever you have added, what do? Subtract again, but lucky for us, because we did completing the square the right way, all the terms are outside the square are not function of x anymore, right? So you can take them out of the integral. So what are these terms? They are 1 over 2 sigma square, 2j omega m sigma square a minus sigma 4 omega square a square. You can make some simplifications for these things, and you end up having the expected value of e to the j omega ax being e to the j omega ma minus sigma square omega square a square over 2. The integral from x equals minus infinity to infinity, 1 over square root 2 pi sigma e to the minus x minus some m, we will call it m bar square, over 2 sigma bar square dx. What is this integration? 1, right? That's the integration of a Gaussian, a shifted Gaussian. Who cares about the Gaussian being shifted? It's just an integration about a shifted Gaussian here from minus infinity to infinity. This ends up being 1. And thus, this is the expected value of e to the j omega x. We return again to phi y of omega because we have had another term outside. That will end up being e to the j omega b plus ma minus omega squared a squared sigma squared over 2. And finally, we will just try to differentiate with respect to omega, this thing. What is the differentiation? It is the differentiation of the argument multiplied by the exponent as it is. So it is j b plus ma minus omega a squared sigma squared times the exponential that is function of omega. When we divide by j and set omega to 0, what is the result of this? We divide by j and set omega to 0. What is the result of this? B plus ma, right? What is this? What is this actually in general? Let's write it just in a complete manner in order not to confuse you. D by d omega the phi y. What is this? What's up? Exactly, right? That's the expectation, right? This is E of y. That's from the fundamental. We have already learned about the characteristic function that the first moment or the expectation is 1 over j d by d omega phi y of omega at omega equals 0. Is the expectation actually this thing? Yes, right? Because the expected value of y is the expected value of ax plus b, is a the expected value of x plus b, which is an plus b. Right? Do you have any questions in anything we have discussed in this first lecture? Go ahead.
Did you take the derivative for the final part? Or?
For what part?
I mean, why did you take the derivative of the field part?
So we wanted to take the derivative of this thing, right?
Yes, why do you want to take the derivative?
Because that's how we will get the moment, right? It's 1 over j, the differentiation of phi y of omega, right? So we took the derivative first, divided by j, substituted omega equals 0. These are the 3 steps to get to the expectation according to the equation from the characteristic function, right? Okay? No questions?
Is this relation valid on linear case or in general?
What relation?
Moment, we get a times a moment of x plus b, but our random variable is also linear. So is this valid in general case? So if we don't have a linear relation between random variable x and y, again we would get this result.
So the linear relation you're talking about is ax plus b, right? So under that case, we got the expectation to be an plus b. If the relation is something else, like y equals x squared, of course, this will not hold. I didn't get your question.
I couldn't explain myself clearly, but maybe later I can ask.
Okay, let's take a break. I will talk to you now about your question. See you in 10 minutes.